Hey there, and welcome. Right now, as you're watching this, there's an invisible force powering your screen, charging your phone, and basically running our entire modern world. Today, we're going to pull back the curtain on that force, electrical power. We'll break down the physics that gets it all the way from a giant power plant right into the palm of your hand.
You've probably noticed this, right? You plug in your phone, and after a while, the charger is a little warm to the touch. Well, that's not a mistake or a flaw. It's a clue. It's a sign of a massive energy transformation happening right there. And today, we're going to follow that energy on its incredible journey.
All right, so to really get to the bottom of this, we've got to start with the fundamentals. Before we can even talk about power, we first need to understand what happens to energy when electricity is flowing. It's a whole story about movement, potential, and, well, change. Okay, think about a waterfall for a second. Water only flows because it's going from a high place to a low place, right? Electricity is kind of the same deal. Charges flow from one point to another because there's an electrical height difference between them. We call this the electric potential difference, but you probably know it by its more common name, voltage. It's the push, the motivation that gets those charges moving. So, as a chunk of charge, let's call it delta Q, moves through that voltage, it starts to lose its potential energy. It's just like a ball rolling down a hill. This formula here tells us exactly how much it loses. The change in potential energy, delta U, is simply the charge times the voltage. And see that little minus sign? That's super important. It's just telling us that the charge is losing energy as it moves from high potential to low potential. So where does all that lost energy go? It can't just vanish, right? Physics won't allow it. Well, it gets converted. It does work. Inside a wire, the moving charges are bumping into atoms, causing them to vibrate like crazy. We feel that vibration as heat. And in something like a light bulb, they vibrate so much that they start to glow, giving off light. Okay, so how can we figure out exactly how much energy is converted over, say, a minute? Well, there's a formula for that too. The total work done, or energy dissipated, is what you get when you multiply the current, I, the voltage, V, and the amount of time, delta T. And dissipated is just a fancy word for converted from electrical energy into something else, like all that heat we were talking about. So now we know how to calculate the total energy used over a period of time, but what's often more useful is knowing how fast that energy is being used. And that, my friends, brings us to the main event, electrical power. Power is really simple when you get down to it. It's just the rate of energy use. How much energy are you converting every single second? To figure it out, we take the total energy we just found, that's delta W, and we divide it by the time it took, delta T. Now here's the neat part. When we plug in our other formula, you see the time variable on the top and on the bottom. They just cancel each other out. And what we're left with is this absolutely beautiful, simple, and seriously important equation. Power equals current times voltage, P equals IV. This right here is the fundamental definition of electrical power, and it's the foundation for everything that comes next. Let's look at this diagram for a perfect real-world example. We've got a cell, like a battery. Inside it, there's this stuff called an electrolyte, and its chemical reactions create the voltage between the positive and negative ends. That's our power source. This power then pushes the current out through the circuit until it gets to that squiggly thing labeled R, the resistor. And it's right there, inside that resistor, that the electrical power gets turned into heat.
So P equals IV is our rock, our foundation. But what happens if you're trying to figure out the power but you don't know the voltage? Or maybe you don't know the current? Well, lucky for us, there's a really famous law in electricity that lets us write our power formula in two other super useful ways.
And the key that unlocks all of this is Ohm's law. It's a classic. It just says that voltage equals the current multiplied by the resistance, V equals I times R. This little equation is the bridge that connects all three of these fundamental electrical ideas. So watch how easy this is. We start with our main formula, P equals IV. Now using Ohm's law, we just replace the V with I times R. So now we have P equals I times another I times R. You multiply those two I's together, and you get our first new version, power equals I squared R. This one is perfect for calculating power that's lost as heat when you know the current. And there it is. This formula, P equals I squared R, is the direct scientific answer to our very first question. This is exactly why your phone charger gets warm. The parts inside it have resistance, R, and as current, I, flows through them, this ohmic loss is unavoidable. It turns some of that electrical energy into heat.
So what happens if we do the substitution the other way? Well, we start again with P equals IV. But this time, we rearrange Ohm's law to say I equals V over R, and we plug that in. That gives us P equals V over R times V, which cleans up nicely to become our second new formula. Power equals V squared over R. This one is your best friend when you know the voltage, like the steady voltage coming out of a wall socket.
Okay, we've got the theory down cold. So now let's use it to tackle one of the biggest engineering puzzles out there. How in the world do we get electricity from a power station, maybe hundreds of miles away, all the way to your house?
And this is a serious puzzle. We have to deliver a massive amount of power. But the very wires we use to send it are going to get hot and waste energy along the whole journey. If you're not smart about it, almost all the energy you generate at the plant could just turn into heat and disappear into the air before it ever gets to a single light bulb.
The villain of the story is resistance. Even the thickest, most expensive copper cables have some resistance. And our ohmic loss formula, P equals I squared R, tells us exactly how we lose that power. The energy wasted as heat is directly related to the resistance of the wire. But look, it's related to the square of the current. That's the real killer. The solution is actually hiding right there in our formulas. To fight that I squared R loss, the number one thing you have to do is make the current, I, as tiny as possible. So how do you send the same amount of power, P, but with way less current? Well, you look at P equals V times I. If you want to make I smaller while keeping P the same, you have only one choice. You have to make the voltage V absolutely gigantic.
And let's put some numbers on that to see just how big a deal this is. Because the loss is based on current squared, the effect is just huge. So let's say you drop the current by a factor of 10, say from 10 amps down to just 1 amp. You don't just reduce the power loss by 10. No, you reduce it by 10 squared. That's 100 times less wasted energy. It's an incredible savings.
And that is exactly why you see those giant metal towers carrying power lines all over the country. The electricity in those lines is at incredibly high voltages, sometimes hundreds of thousands of volts. Power companies use transformers to step up the voltage way up high for the long trip, which keeps the current and the losses super low. Then, when it gets to your neighborhood, other transformers step it down to the safe 120 or 240 volts that we use in our homes.
All right, we have gone through a lot, I know. So let's just take a second and put all of our essential formulas together in one place. Think of it as your new power toolkit.
Here it is, your cheat sheet. And just remember, these 3 power formulas aren't different laws. They're just different ways of looking at the exact same idea, all connected by Ohm's law. P equals IV is your home base. P equals I squared R is your go-to for calculating heat loss. And P equals V squared R is what you grab when you know the voltage.
So the next time you drive past one of those huge transmission towers, or you feel your phone charger getting a little bit warm, you'll know the elegant physics that's going on behind the scenes. It really makes you stop and think, what other invisible forces are out there, hiding in plain sight, just shaping our entire world? Thanks so much for joining me.